So let's review the dynamic force analysis method uh, using the example of this 4-bar mechanism. We have seen a 3-bar crank slider and a single rotating link, and we have seen how we can use sigma f equals 0 and sigma t equals 0 to, or if we are writing in terms of newtons instead of D'Alembert's principle, we can write this as MA and I alpha, where I is about the center of gravity. So we have seen how to use these in order to form the set of equations to be solved to get the dynamic force analysis done for various, well, at least we have seen two examples in the class, and we'll quickly look at a couple more examples, maybe 3 examples. So here, first thing we will do is separate into free bodies. In this 4-bar mechanism, the force F is being applied at a point P. These little circles with these black and white yin yang style patches are the center of gravity for each of these links. So we can separate these out. We can draw a free body diagram for each one of these links and identify what are the forces at the joints or at specified points where external forces are acting on them on the body. So this is link 4. We have a torque T4. We will have a joint reaction at this, which will be F14. Then there is a joint reaction at this, which is F34. Other than that, we will have from the CG, we will, at the CG we will have some acceleration of this body 4, and we can identify where are these positions. Let's say this position, for instance, I'll use a different ink to mark this. This position is R3 with respect to the center 4, and this position is R1 with respect to 4. That is where the um, forces are acting. We know that if we consider the ground here, then this will be equal and opposite. 4 1 is equal and opposite to 1 4. We know that at this point this will be F4 on 3 equal to minus 3 4, and similarly here there is an external force that acts at point P. From the CG, this point P is at a position RP. We also have this point here where there is a joint reaction coming from link 2 on link 3. This should be equal to minus 3 on 2. There is an external force P which is acting on this FP, and then at this point there is going to be an acceleration a g of body 3. There are no other forces, so we can identify again position of this point as R2 with respect to 3, and we can identify the position R4 with respect to 3. So maybe just to keep things clear, I'll mark these forces in black. Then we can look at this link here. We know this is going to be, okay, let's go back to black. This is going to be F32, and there is a CG here which will have some acceleration. This is a G2, and then there is a reaction force F1 on 2. We can mark the positions of the point where this F32 is acting is F3 R3 with respect to 2, and where this is acting is R1 with respect to 2. At the pivot, we know that there's an equal and opposite F2 on 1. This is sorted. Then from here, we can look at what are the equations at each body. We can start uh, considering, let's say, first body here, I mean body 2, body 3 and body 4 are 3 bodies. We will have 3 equations in each, so we can expect 9 equations, and we will be able to solve for 9 unknowns. Then we can write, say, for body 2, we can start with F12 in x direction plus F32 in x direction should be equal to M2 times AG2 in x direction. And then we'll have F12 in y plus F32 in y should be equal to M2 AG2 in y direction. So we are essentially taking the local coordinate system for this at a convenient point. We can consider a local coordinate system here. We can then also similarly, we can consider a local coordinate system here. We can consider a local coordinate system here for these individual bodies. So these are non-rotating coordinate systems. These are local non-rotating coordinate systems. Based on the local non-rotating coordinate systems, we can write uh, the x and y coordinates of any of these forces for any given position of this 4-bar linkage. Then we can write the torque equation similarly. So if we are considering the body number 2, so you have a torque T12 which will act to ensure that there is dynamic equilibrium against these forces Fp and T4. So we have to assume that there is a torque T12, and maybe we'll assume it to be uh, a positive torque. Then as we proceed through the computation, if we find it is going to have a value of, say, minus some numeral, then we can adjust the direction accordingly. So T12 plus, we have to write for 2 forces, we have to write the moments. So we can write R12 crossed with F12. These are vectors which have x and y components, and we've seen in class how we can write this, or you know how to take a cross product of 2 vectors. And then this will be summed up with R32 crossed with F32. This should be equal to the moment of inertia about the CG times alpha of the link. So if this is going at, say, alpha 2 and omega 2, we can directly relate those to the through the moment equation. Similarly, for the link 4, we can, or maybe we'll go for link 3. And link 3, we know there is F23 x, so we can write that in terms of F32. So we have F32x, which with the minus sign, plus F43 in x direction, and there is Fp in x direction. This should sum up to M3 Ag3 in x direction. Similarly, we can write 32y, 43y, and Fpy. Sum of these should be M3 Ag3 y direction. Last but not the least, we can write the moment equation also. You can take R43, take a cross product with F43. This, and then subtract R23 crossed with F32. Normally I would have added it if it was F23, but we are taking F23 to be minus F32, so that we reduce one So it's a known, it's not an unknown. We are just writing it in terms of something we already know, because we know f23 is equal to f minus f32. Otherwise, the matrix that you will build will end up having this as a separate equation with a lot of zeros and a 1 wherever there is a coefficient for f23. So we want to avoid that situation. So we are simplifying the equations as soon as we know that there is some well-established relationship between two of these values that are unknown. Then this plus, there is rp crossed with fp, and all of this should be summed to ig3 alpha 3. And then we can write for the last body, we have summations would be f, we have 4 3 x plus f4 1 x plus well, those are the only two. Those two summed up will give m4 ag4x. Then there is f, well, I should have written f34x and 14x. So f34x plus 14x gives this. You can have f34y plus f14y is m4ag4y. And then for the torques, we can write r14 cross f14 plus r34 cross f34 plus t4 should be equal to ig4 alpha 4. Those are the 9 equations. Of course, just like earlier, instead of, so we had f32 here, so we retained f32 so that we can avoid the f23. Similarly, we can retain f43, and instead of writing 34, we can then replace this equation as minus f43x plus f14x is equal to m4ag4, as I was trying to do earlier. I had not included the minus sign, so that would have been wrong. However, yeah, this is perfectly fine. We are avoiding f34. Instead, we are using this relationship and using f43x. Similarly, this would become, instead of this, I can write minus f43y plus 14y. This should be equal to this. And here, this can be replaced with minus f43. So we'll end up changing this term to minus term. Note that every time I've been taking a moment, I'm considering the position vector with respect to a CG going to the point, towards the point where there is a force applied, and then using the force as is. So I'm not shifting the force. For instance, here I'm not shifting the force to f14. That would be wrong. I can write minus f41, which is fine, but I cannot just write f14 in this direction. Now, once I do a computation through by solving all of these 9 equations for 9 unknowns, if I find that the value of f14, for instance, if f14 equals minus 9 newtons, then the corrected diagram would show the other direction, or other sense. Otherwise, whatever I've assumed, based on that, I will split this into the x and the y components. So this will be x and y components of f14. All right. I hope that explains the 4 bar in sufficient detail, how we have written all sorts of equations necessary for solving um, for the dynamic force situation or dynamic equilibrium situation. Note that the unknowns, maybe I'll just point out which are the unknowns here. We don't know what is the torque T12. I'll try to use a color which I've not used so far. Let's see, is this visible? Yeah, So T12 is unknown. We are trying to find T12. We don't know the reaction force F12. So it's not just X, but it is also X and Y. Here we will consider these are the two unknowns. Then we don't know 32X, 32Y. So we don't know T12. So maybe I'll just mark them only on the equation so it is easy to keep track of. Then so 32 I've already marked, so I'm not going to mark again. We don't know 43X and 43Y. Here we know all of them. We know FP by direction and magnitude, so this is not an unknown. We know T4 is not an unknown. We have already marked 3, 4. We already marked 4, 3, so we are not going to mark that again here. We don't know 1, 4 and 1, 4 X and Y. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 equations, 9 unknowns which can be solved. You can put all of this into a matrix form by listing out all the coefficients of unknown terms on one side and writing all the unknowns as a vector, and then writing all the known quantities on another side. So for example, if I have to write this equation in this form, it will become I can write f12x, f32x, there can be f12y, f32y, there is t12, and then there is f43x, f43y, and the last set, I believe that was 14, yeah, 14x and y. So it's f14x and f14y. Can I move this slightly? Yeah, f14y. So in this, I know the coefficient of f12 exists. For 32 it exists, but there is nothing else. So these are all zeros. How many ever zeros are required to fill up this hole? So this should be a 9 by 9. This should be a 9 by 1. And then there is a 9 by 1 which is known. That value is M2AG2X. Similarly, the next one will have 0, 0. There is F12Y and there is 32Y. The remaining are all zeros. So maybe I'll just write the exact number. 6, 1, 2, 3. And then this becomes M. Yeah, like that. You have to now carefully write for this. The fifth one is going to be 1. And then you have to expand this into R12X F12Y minus R12Y F12X. So for that you will get terms. For 12Y you will see R12X, and for 12, so 12X was also there. F12X is also there. For that you will see a term which is minus R12Y, and then so on. So you write all of these, so you populate this 9 by 9 matrix, and then for these unknowns you can invert this matrix and multiply by these known quantities to get what are the forces and the torques.